Good evening and welcome to NASA's Asteroid Initiative Idea Synthesis Workshop. We're broadcasting live on NASA TV from the Lunar and Planetary Institute in Houston, Texas. Over the next couple of days, we'll be talking about the 96 ideas that were selected from more than 400 responses to NASA's Asteroid Initiative Request for Information released back in June. For those of you tuning in online, we actually have chat rooms set up, and the workshop hashtag is NASA Asteroid, and we'll have hashtags for each topic session. We ask that you actively participate and keep the conversation going. All the virtual participation options are available at nasa.gov/asteroid workshop. And now it is my pleasure to introduce Dr. Stephen Mackwell. He's the director of the Lunar and Planetary Institute.
Thank you. It's a great pleasure to welcome everybody back. It's only been, 51 days for many of you. For those of you who are here, just before October began, welcome back. We put on some rather cooler weather for you, which is nice. It's a pretty time of year in Houston. The meeting that we started 50 days ago was a very interesting, exciting meeting. I think it was great turnout of people, great flux of ideas. It was a great beginning to this meeting, and I think we really do have the stage set for a very exciting couple of days here, and I'm looking forward to hearing the presentations and seeing what we can do here in the next couple of days. But it's obviously it's a very important and vibrant topic, and one with a lot of opportunities going forward. So welcome again. I would suggest that tomorrow at the end of the sessions, I guess the session kind of ends up sometime around 5:30 or something like that tomorrow, or the two sessions are going to end up around then. Tomorrow evening, and this is purely coincidence, we didn't do this, but tomorrow evening, David Kring, one of the scientists here at the LPI, is giving a presentation at 7:30. It's a public presentation on the 2003 Chelyabinsk airburst and the hazards of near-Earth asteroid impacts. And that's going to be on in this room tomorrow evening at 7:30. It's a public kind of presentation, so the level is going to be pitched fairly broadly. David is a good speaker, so it should be pretty good. And afterwards, there'll be refreshments out in the great room here. So everybody, of course, is welcome to disappear quickly for dinner and come back for that if you wish, just continuing the theme of asteroids along. One final thing I have to do, and it's a requirement that I do here, is that for those of you who heard it before, if a fire alarm goes off, leave, okay? We have fire exits at the back. I'll tell you, if the fire alarm goes off, you will know the fire alarm went off. We actually had alarm go off the last time when we started. That wasn't the fire alarm. That was the quiet one. The real fire alarm will have you out of the building very quickly. The easiest way to go is out through the doors here and back out through the foyer and out into the parking lot. There are also fire escapes at the back here. The only other thing I have to mention, and you probably all know this already because most of you have been here already, bathrooms down the corridor over there. Down that hallway you'll find bathrooms. There's also bathrooms, a couple of bathrooms just in the back here. So I know everybody online really needed to know that. So with that, thank you very much, and I'll pass it back.
Thank you, Dr. Mackwell. Next up, we have Michelle Gates from the Human Exploration and Missions Operation Directorate at NASA headquarters. Michelle is going to give us a brief overview of the workshop objectives.
Hi, welcome back. It's very unfortunate that we were so abruptly cut off the last time we all met. But we're very excited to continue with what was very important to us, as well as many of our stakeholders. And so what I thought I'd do today is just give a couple chart overview of some of the stuff we talked about last time in the plenary session, and then briefly review the objectives of the workshop, as well as the charge to the session chairs for the closing synthesis session on Friday morning. So you'll remember that there are two aspects of the Asteroid Initiative. One is the Grand Challenge. Jason Kessler and Jen Kustetic, who are here, I believe, are going to be leading that. I think there's 3 sessions in this workshop on the Grand Challenge, which includes next slide, finding all asteroid threats to human populations and knowing what to do about them. So I know Jason and Jen are very much looking forward to getting started in this workshop with finishing up what was important to them in their planning that we started in October. The other aspect of the initiative, as you know, is the Asteroid Redirect mission. There are elements that are unique to each, and there are elements that are common and leveraged for both. So they're really a synergistic whole. You may recall this slide as well, which talks about the near-term strategy for the Asteroid Redirect mission, which includes leveraging ongoing activities in the Science Mission Directorate, which we have called the Identify segment of the mission, which includes studies and trades right now, as well as upgrades and observation assets that Lindley Johnson will be talking to you about a little bit later this evening. In the Redirect mission segment, there is a reference mission that is currently being studied, as well as an alternate mission, and we're looking forward to your ideas, hearing those in this meeting, as well as your thoughts and inputs in the synthesis session. The last segment is the Redirect Crewed mission, which includes leveraging the activities that the agency has going on right now, the Orion and SLS vehicles, and how we can use those beyond the moon to accomplish this compelling mission. Steve Stitch is going to be speaking after me in detail about that and sharing some updates as well. We have evolved our thinking on the mission objectives, and we have listened to the feedback that we have received to date. So I wanted to share with you today, this is actually the first time that I think we've talked broadly about this, but the primary objectives that we're currently planning to and doing analysis against are human exploration in the mid-2020s to an asteroid that prepares for future exploration activities, technology demonstration of advanced solar electric propulsion, and enhanced detection and observation of near-Earth asteroids for planetary defense. Those are the 3 main areas that we're looking at as the primary objectives of the mission. There are many secondary benefits and objectives, as you have heard previously, and that we have talked about broadly at length, as this initiative is so broad. And that includes asteroid deflection demonstration or proof of concept, which is another aspect of planetary defense. Lindley Johnson, again, is here and going to talk about that. Science benefits, international partnership opportunities, commercial partnership opportunities, and that includes, for example, in situ resource utilization. There's also some ground rules that we've been taking in our analysis as boundaries, including affordability, manageable risk tolerance in technical risk, and programmatic viability. We currently have 3 internal mission studies going on. One is the reference robotic mission concept, which again is to redirect a small near-Earth asteroid to a stable orbit in the lunar vicinity and potentially demonstrate asteroid deflection. The study is being led by the Jet Propulsion Lab. It's NASA-wide, and there's significant involvement and partnership with the Glenn Research Center in that study. We're also looking at an alternate concept to redirect a small mass from a larger asteroid and potentially demonstrate potentially hazardous asteroid size deflection. This study is being led by Langley Research Center. It also includes many of the same members as the previous study, and so we're looking forward to how both of those turn out, as well as evolve with the ideas in this workshop. The crewed mission is being looked at by the Johnson Space Center, and again, Steve Stitch will talk to you more about that when he comes up. This slide is just a brief summary of our current status, which has evolved since the first day of the workshop that we had previously. We have charted a robotic concept integration team. That team is being led by Jim Ryder from the Marshall Space Flight Center, who's sitting over there. Just raise his hand. He's also the chair of the redirect session, which was held last time. Consistent with our guidance, our acquisition strategy foundation is to leverage ongoing work, and y'all are well aware of that. We do want to pursue partnerships and participatory engagement. This workshop is a part of that, and we have some internal status briefings scheduled and are planning an industry day for the spring of next year in which we'll share our status as a result of near-term decisions, including this meeting, planned updates to FY14 plans, as well as communicate our plan in the 15 NASA budget. We did want to emphasize this time that we believe this activity does advance existing policy goals. There's a list that you can read at your leisure, or we'd be happy to talk about. There are several areas of bipartisan policy that this initiative is responsive to. Chris Moore will talk to you more this evening about a summary of the RFI results, as well as the review process. And here's the core. Why we're here at this meeting is to hear what you have to say. We want to examine and foster a broad discussion on the ideas coming forth in this meeting, as well as discuss, debate, and synthesize a set of findings that we can take back and use within NASA. Our NASA personnel will serve as leads in our discussions, but we ask for your active participation. You'll see in the workshop sessions the seating is auditorium styled, but that is just due to space limitation. Please have open discussion. Please feel free to speak up. We have already read the RFIs. We really want to hear what you have to say and what you think, including the folks online. There's chat rooms, there's Twitter. We've got facilitators and moderators who are available in the sessions to help with that. And so Friday morning, we'll be hearing a synthesis results of each session presented to us by the session chairs. They've been given a request for specific areas to bring out of the session discussions and present to us. This is a summary chart here, but Chris Moore is actually going to talk to you a little bit more about this when he gets up. That's all I have.
Thank you, Michelle. Next, we're going to hear from Steve Stitch. He's the Deputy Director at Johnson Space Center here in Houston. And as Michelle stated, he's going to talk about the Asteroid Redirect mission with a focus on current activities related to the crew portion.
Thanks, Wendy. Before I get started, I'd like to thank Dr. Maxwell and the Lunar Planetary Institute for hosting us again here. I think they have treated this very well. We're not like in-laws or something that won't leave, but thanks very much for hosting us again. And also on behalf of the Johnson Space Center, Ellen Ochoa and Kirk Shireman, the Center Director and Deputy Center Director, I'd like to welcome everybody here to the Asteroid Workshop. I'm going to try to talk a little bit tonight about what we've been doing relative to the mission, and also sort of frame it in the context of the capability-driven framework and how what we're doing with this first exploration mission as one mission in a series of missions, we're trying to take capabilities that we're building across NASA, across HEOMD, across the Space Technology Mission Directorate, and pull those together into a single mission. If you look at this image, this is a pretty bold mission. If you think about this time frame in the early 2020s, some 50 years after we would have flown the Apollo missions, we will send 2 crew members further into deep space than they've ever traveled before to obtain some samples from an asteroid that we've moved there using a robotic spacecraft. So it's a very ambitious mission. As a former shuttle flight director, I think about this mission, and I think, wow, it'd be great to be on console for this mission. So within HEO, we're really operating on 6 principles in terms of putting together our exploration plan. We need to execute our missions within a sustainable budget. We realize the situation relative to the budget, and so we have to keep that in mind as we build our missions. We're trying to take high TRL, very mature technologies that are ready to be infused into a mission and bring those together into a compelling mission. We're also looking for near-term opportunities to fly in space, to push forward in deep space relative to eventual goal of sending humans to Mars in the 2030s. And then we also look for opportunities to bring our commercial partnerships along and commercial business to further enhance that industry as well. We've had great partnerships on the International Space Station with commercial cargo, and so we see this as another avenue that's very important as we build our strategy. And then we're looking to put together infrastructure in space that's used for a long time, that can't be kind of a single purpose mission, but it needs to kind of feed forward to deep space exploration. And then again, we want to work strongly with our international partners and leverage the partnerships that we have on the International Space Station today, and also our commercial partnerships as we move forward. So our overall purpose is to move forward from the left part of the slide, where today in the shuttle program and then in the International Space Station program, we've been operating very well and doing a lot of great research and exploration on the International Space Station, but we're very much in what we would call an Earth-reliant centric model, where we're very dependent on resupply from the Earth. We need to move to that final destination, which is Mars on the right-hand portion of the slide, which is Earth independent, where we need to be much more on our own in terms of not having that supply chain from the Earth. And the way we're going to do this is we're going to move into this proving ground, which in the middle of the slide you can see the moon and cislunar space, and you can see the slide that shows the Orion docked to the asteroid redirect vehicle and how we would move into that area to begin to buy down the risk. If you think about today on the International Space Station, the crew is a mere 1 or 2 days from returning to Earth. And in fact, if there were an emergency, they can be back to the Earth within hours. As we move into cislunar space, those transit times are on the order of, depending on the time chosen, somewhere on the order of 6 to 12 days to return back to the Earth. And then if you think about Mars, those transit times are on the order of 6 to 9 months. So we're kind of moving out, if you look at it in terms of a sailing ship, we're moving into that deep waters much more slowly as we evolve our capability to Mars. It all starts with the International Space Station. Of course, today is the 15th anniversary of the first element launch, which was Zarya. If you think about where we started 15 years ago, it was incredible. We only had 44,000 pounds of hardware in space. Today we have an International Space Station that's a little less than 1 million pounds of hardware. And today the things we're doing on Space Station feed directly toward exploration. We're testing human health and performance. We're embarking on longer and longer crew durations. We're trying to understand how the human body performs in space in terms of cardiac performance, bone loss, how to sustain the human body in space. Eventually in 2015, we'll fly a 1-year duration, which is kind of building up with 2 crew members, building up toward Mars. We're also using the space station as a habitability and logistics test bed of how we would work those kinds of things for moving on to Mars. And then it's a technology test bed where we're testing things like a docking technology. How do we do closed-loop life support better to sustain a crew all the way to Mars? Those systems are in their infancy, and they're working well on the space station, and we need to use those systems, improve those systems on the space station to build forward. Also, we can look at how well hardware performs in space for long durations. The Zarya element and the node have been in space for 15 years, and so we can understand the performance of those systems as well. And then, of course, today we're in the process of turning LEO over to commercial endeavors through commercial cargo and commercial crew programs. In fact, this week on Tuesday, we released the request for proposals for the commercial crew, next phase of the contract, so we're moving out in that direction as well. Now, our programs today in exploration are not just about paper designs, not just about analysis and documentation, but we're really moving into a phase where you can see our hardware beginning to take shape. You can see the next launch vehicle beginning to take shape and the Orion spacecraft as well. In this slide, if you look at the upper left, you can see we've had already 3 successful ground tests of the Space Launch System development motors. These are derivatives of the shuttle motors. So again, we're taking capabilities we've had in the past and building them up into the Space Launch System. We've got on the upper right hand, you've got the core stage computers being installed and ready for testing very soon on the test bed, the flight test bed in the Marshall Space Flight Center. At the Michoud Assembly Facility in the bottom left, we're doing friction stir welds on the barrel section. The tank is derived from shuttle technology, but we're using modern manufacturing. And then we're about to get very soon back into RS-25, which is a derivative of the shuttle main engine, testing on the test stands at Stennis Space Center. The inlet conditions are slightly different for the SLS rocket. So the Space Launch System is going to be a very versatile launch vehicle. It really is the key to enabling missions in deep space. It will lift up to 25 metric tons to the cislunar environment, to the DRO environment, which I'll talk about a little longer, and then it's up to 70 metric tons to low Earth orbit with initial capability, which is evolvable to up to 130 metric tons. When we turn to the crew vehicle, Orion is beginning to take shape as well, and I'll talk a little bit more about how Orion will be very beneficial for this asteroid redirect mission. We had a very big milestone recently at the Kennedy Space Center where we've done power-on testing in the upper left-hand corner of the slide for the Orion Exploration Flight Test 1 configuration. We're bringing those systems online, we're powering them up, exchanging data, and letting the computers send commands out to the various propulsion elements and various other pieces of the vehicle, so it's a very important milestone. We've done 9 parachute drop tests for Orion to date, and we've done a variety of configurations here you see the 3-chute cluster. We've done 1 parachute out, we've done a single drogue chute. We've done a variety of tests to stress the envelope of this system, and so far the performance has been very well. We've been sharing this data with our commercial crew partners. They're using some of the same technology, so again, we're making great progress there. On the upper right, we've done water landing tests with the vehicle to understand how it performs and floats in a water environment. At the bottom left, you can see the heat shield, which is up at Textron near Boston, and it's finalizing its preparation for being shipped to the Kennedy Space Center later this month. We've put together the back shell for the Exploration Flight Test 1 unit in the on the bottom row in the middle slide, and that's progressing well. And then recently out at Sunnyvale, we've done the fairing SEP test. These fairings are on the service module and actually help carry the load. Those separate during powered flight. Very important for those to perform well, and we've completed that test. This is all moving toward Exploration Flight Test 1 in 2014. So this is real hardware coming together, which would be the first test of the Orion heat shield in the actual environment. We'll get up to about 60 to 70% of the cislunar speed required for entry. It does 2 revs around the Earth. We'll also get a little test of the on the Delta IV Heavy. The upper stage has a lot of common components to what we're going to use for future exploration missions, so we'll get a great test of that. The hardware is coming together, and the vehicle will be readied in the springtime. So this is a real mission, real hardware moving forward in exploration. This leads us to EM1 in the 2017 timeframe, and this is the first integrated test of the Space Launch System with the Orion vehicle. We've recently changed the mission. We've baselined this distant retrograde orbit, which you can see on the right-hand part of the slide. That's the kind of orbit we're going to need for this asteroid redirect mission. And so we see this test flight uncrewed using the trajectory, simulating the trajectory in the distant retrograde orbit is very beneficial. We can learn how to target all the burns, the navigation required for each of the burns. It'll be a good dry run from a mission perspective for the asteroid redirect mission. So this is a recent change and very important. Now as we move into the asteroid redirect mission, you can see the mission uses the SLS and Orion vehicles. So Orion heads out to the distant retrograde orbit, which is a great orbit about the moon that we found that it's called retrograde because it kind of travels in the opposite direction of the moon's orbit, but it's a very balanced place to be. It's a good place for us to bring the asteroid to, and also we can get there with Orion. We'll dock to the robotic spacecraft with Orion, and then we'll perform 2 EVAs, and we'll talk a little bit more about that in detail. And then, of course, the main objective is to get a sample from the asteroid and then bring that back in Orion. So this will try to build upon some of the capabilities we have in development. So I've talked about the Space Launch System. I've talked about Orion. What we're doing with the rendezvous and trajectory work is we're building upon capabilities that we've had on previous programs. Here you can see on the right-hand part of the slide what the trajectory looks like. It takes about 9 days to get out for this particular launch date to the distant retrograde orbit where the asteroid robotic spacecraft will be. We use a lunar gravity assist on the way out, which we've taken that trick from many of our scientific missions that have used that, and it slingshots us into this distant retrograde orbit. We'll spend about 5 days there doing a couple spacewalks, and then we'll return. The return flight time for this particular launch date is about 11 days. And again, we'll use a flyby of the moon on the way back. It'll be a spectacular view of the moon, flying by at about 100 kilometers. On the left-hand side, you can see we're trying to leverage a lot of the work that we've done from the Space Shuttle program. Toward the very end of the shuttle program, we flew a variety of sensors on board the shuttle in parallel with the system we used to do the approach to station, to test their performance. We're utilizing some of those sensor systems for both the robotic vehicle. We're looking at the commonality between that sensor system for the robotic vehicle and Orion. So we're leveraging that technology. There's a lot of synergy between those two. And then we're continuing to work and refine how that system performs relative to the trajectory, and we've done testing with those sensors. So this builds on real sensors that have flown in space before. In terms of the docking system, so this is another thing. If you think about the rendezvous sensors and trajectory, that feeds forward to exploration. All the destinations are going to require an approach to another object in space. The docking system is the same way. We're leveraging a lot of the work that we're doing today on the International Space Station. It's kind of a two-phased approach where we're using this International Docking System standard on the International Space Station. That's completed a PDR recently in the September preliminary design review in the September timeframe. They're working toward a critical design review next summer, and then the delivery of hardware in the 2015-2016 timeframe. That you can see on the upper right, there's a couple of locations that are going to be utilized on the International Space Station to allow the commercial crew vehicles to dock. We're taking that same hardware and we're feeding that forward to the Asteroid redirect mission. On the left-hand side, you can see the active docking mechanism extended. That'll go on the Orion spacecraft. Kind of in the center of the slide, there's the passive mechanism that goes on the robotic spacecraft. So it's a phase 2 approach for the docking system. So we're feeding that forward to space station. If you look at the way we're going to transport this to the International Space Station, we're going to use the Dragon cargo vehicle to bring it up. So we're combining our commercial crew program, International Space Station, and exploration together to put together the docking system, which then feeds forward to the rest of exploration. Now I'll talk a little bit about EVA. Whoops. Our EVA development. And this is a very important part of the mission. So we have a video we'll show. And this shows the crew coming out of the Orion spacecraft. Orion will serve as the airlock for the Asteroid redirect mission based on our concept. They'll use some very simple poles to traverse across to the robotic spacecraft. And it looks very simple in the video and animation. But we've spent a lot of time already in our neutral buoyancy laboratory here in Houston simulating these very techniques. You can see a crew member practicing egress from the Orion hatch in our modified AIISW, which is a little bit like a Gemini spacesuit. And now you can see the next phase of the EVA would be to traverse across the spacecraft. Here you can see Rex Walheim, a mission specialist that flew on STS-135, traversing across a set of handrails. It's actually space station hardware in the neutral buoyancy lab, but he's practicing that same technique to understand the suit performance. You can see a lot of the hardware on the suit is derivative from shuttle and space station, and the suit is a derivative from the shuttle entry suit. And now you can see this again is Rex trying to see what kind of tasks he can work on. Here he is in the neutral buoyancy lab using something called a portable foot restraint, and he's installing it in a socket, which he would typically do, and these are the kind of tasks we might need to do on the Asteroid. So again, we're in the neutral buoyancy lab trying to understand the performance of this suit, and the suit is a very important early part of the mission. Here you can see one of the next tasks would be to set up the crew member in position to extract the samples, and here you can see Rex Walheim again in the NBL managing his tether and practicing traversing across a simulated part of the asteroid. And so we've completed a total of 8 tests in the neutral buoyancy lab already in the suit, and we have about 6 more planned for next year. Next year we'll move into a little bit higher fidelity phase. We'll upgrade the suit, try to improve the performance of the suit. In September we did two 4-hour runs to try to prove out the duration that we might need for the mission. Here you can see the crew members doing some photography and then starting to extract the samples. These are notional videos, and here you can see Rex in the NBL doing some pretty delicate tasks. We've got the same gloves on the suit that we use on space station today, and so we've made that change to the suit. So again, real progress this year, more planned progress next year, and here you can see Rex in the NBL going after another sample and putting it in a bag. And you can see it's tethered just like we would execute in the real asteroid redirect mission. So again, real progress on spacewalking. Now we'll talk a little bit about the primary life support system that enables this technology. We have an advanced exploration system project that's looking at an advanced spacesuit life support system. They've been working for several years. This past fiscal year, they completed a prototype of that system, and it's in testing here at the Johnson Space Center. We've got, if you look in the upper right, you can see what looks like a crew member next to the PLIS, which is in the two brackets on the upper right. We've got this metabolic simulator, and we're into testing already on this PLIS, and this PLIS feeds forward very well. This primary life support system feeds well for both on Mars and other missions. And then at the bottom right, you can see the kind of modifications that we need to perform to make the modified advanced crew escape suit functional for this mission. Helmet lights, backpack cameras, display module. We're already working on the design for where we would put those things, how we would interface them to the suit. So that work is ongoing today. So again, in terms of suit, we're leveraging technology that we're working on today, trying to integrate that into the mission, and then looking how that feeds forward toward exploration. And then the same thing with our high-powered solar electric propulsion system that enables the asteroid to be brought back to the distant retrograde orbit. Today, that system would be on the order of 40 to 50 kilowatts using 3 13-kilowatt thrusters. That then feeds forward to exploration into the 90 to 100 kilowatt with the same kind of thrusters, and then that evolves to what we would need for cargo delivery to Mars, for example, on the upper right, which is on the order of 250 kilowatts, using a little bit higher powered thrusters. And in the bottom, you can see that we're currently under our Space Technology Mission Directorate working on solar array technology. That's real funded work within the agency, and also thrusters and power processing units. So here we're taking a capability that we're working on in the Space Technology Mission Directorate and infusing that into this asteroid mission, then that feeds forward for exploration. And then finally, how does this mission feed forward to Mars? This chart across the top shows the different kinds of missions, the current mission on ISS, the asteroid redirect mission, and then longer stays in deep space, and we're working our way out to Mars on the upper right. You can see that each of these things that we're doing sort of build in a stair-step fashion to get us further into space and then build capabilities for the next mission. So again, we're trying to slowly work our way into the solar system and use this mission as the start. At the bottom, you can see ISS provides the deep space habitat, life support, and autonomous assembly that we've been working on. That feeds forward to all the different Mars missions. For the asteroid mission, we add those pieces of the Space Launch System to get heavy lift, which we need to get cargo beyond the Earth's gravity field. We get the Orion high-speed entry capability. We get exploration EVA, and then we get this solar electric propulsion capability, which enables exploration. And then someday, we continue to work on the other pieces at the top to build these stepping stones to Mars. And finally, how does this enable exploration? You can see on the right-hand side 3 different kind of visions of how this feeds forward. The upper right slide shows continued utilization of the asteroid in the distant retrograde orbit with what we call an exploration augmentation module concept. It could be provided by an international partner or commercial or NASA provided, but it would extend the stay time in the distant retrograde orbit. You can see our international partners in particular are very interested in lunar missions, and you can see in the middle slide on the right how that then would feed forward to a potential low lunar orbit kind of campaign. And then at the bottom, you can see how this feeds forward to deep space. So again, I won't read through these, but you can see how this builds the systems we need for exploration on this first exploration mission. We get Orion and SLS, we get solar electric propulsion, and then we get deep space capabilities like rendezvous and docking and EVA, which then feed forward. So that's a little bit about what we've been doing here at the Johnson Space Center. We look forward to the session tomorrow at 1:30 to get your ideas as well. Thank you.
Thank you, Steve. Next up, we have Brian Wilcox. He's from NASA's Jet Propulsion Laboratory, and he's going to discuss the latest work in the asteroid redirect mission, the capture system design and analysis.
Good evening. For the next few minutes, I want to talk to you about the capture mechanism and process envisioned for the so-called reference mission that Michelle described earlier. And this, if people on the web can see my laser pointer, basically it describes the bag going over the asteroid, which you've seen in the animation that was released during the summer. I'm not going to replay that animation. It's a great animation done by the Langley Research Center. But I'm going to talk about the details of that process. The thing about the asteroid capture process, and the reason we're focusing on it tonight of all the subsystems on that reference mission, is that it's the thing that really hasn't been done, and it's the thing that strikes many people as quite sporty. And so we need to pay attention to the possibilities of what we might confront when we get there. First thing, we don't know a lot about these asteroids. Many of them are probably rocks. That is, the ones that turn out to be meteorites when they hit the ground because they made it through the atmosphere are the more competent ones. There's lots of reasons, however, to believe that the meteors that enter the atmosphere, that many of fragments don't make it to the ground, is because that they're not very competent. And so they could be in the form of dirt clods, and we do see pieces of asteroidal material that do make it to the ground that have much the consistency of dirt clods. And then there are also quite possibly just grains of sand that are bonded together by molecular forces that are extremely weak, and where the slightest touch would break up the object. So that led us to focus on the bag because not only did we want to confine the whole asteroid and bring the whole thing back, but we also wanted to protect our solar arrays and our optical surfaces and our radiators from contamination. So all the ideas that you might imagine, harpoons and lassos and side, when we considered that aspect of the problem, that it could well be one of these rubble piles. Some people have called them sandbars. The other aspect of it is the spin state. Certainly many of them do spin very slowly, hours, rotation period. But some do, many of them do tumble, and the smaller they are, the more likely they are to tumble, because the time to relax to a principal axis spin is long compared to the time between collisions, in fact long compared to the age of the solar system. So for these small objects, we would expect them to in many cases be tumbling. And the one that gives us real pause are the ones that are spinning fast and tumbling, the ones that are in excess of 1 RPM and tumbling, and you'll see in a few minutes why that is. The distribution of spin states has been mapped. This is maybe a year old. I think there are a few more objects that have been identified. But most of the larger objects, here we have absolute magnitude, which is basically an astronomer's way of saying how big it is. And in the box we have the range of interest to us, which is about 5 to 10 meters in diameter. The bigger objects tend to be clustered just below the so-called spin barrier or rubble pile limit, where the gravity is equal to the centrifugal force at the equator. And that is one of the things that leads people to believe, the fact that there's so many clustered right up to that limit and very few beyond it, that there are many of these objects are very weak. But as you get smaller and smaller, that spin barrier no longer appears to be a major constraint. And you do see objects spinning faster, and at the 1 RPM, you see a few objects have been discovered that are faster than 1 RPM, but many of them, most of the population of interest to us, is spinning slower than that. So one thing we could do is we could just say, well, we're not going to go after any fast spinners, but it's incumbent upon the team to evaluate whether indeed, we have to make that constraint, because we'd like to, if we find a great target that just happens to be spinning fast, we'd like to be able to go after it. The current thinking of the bag is to have these pie-shaped wedges that we can inflate interior to the bag and thereby grab the surface of the asteroid. If it is spinning rapidly, we could grab that surface quickly and apply a pressure comparable to the yield strength, the tensile strength of the the asteroid, a fraction of a psi, and yet over the huge, surface areas that we're talking about, many tens of square meters, we would have the forces that we need to despin and detumble those objects. So we have an inflatable exoskeleton that deploys the bag, and then we get the asteroid into the bag, and then if it's a fast spinner, we would deploy those bags to quickly capture it. So if it's a slow spinner, we would bring it into the bag, but then just use cinch winches to pull the bag closed. So these winches, very much like fishing reel winches that basically have a slip clutch so that if the fish wants to run, it can run, because after all, you have a 1,000-ton object, and if it wants to do something, it's going to do it. So you basically have these winches with slip clutches that you can gradually close the bag over it as the air is bled out of the system, as the gas is vented. And you don't need to deploy, if it's a slow spinner, you don't really need to deploy these interior bags. But if it's a fast spinner, then the feeling is you would deploy these wedge-shaped bags in a very rapid time. In vacuum, of course, these bags deploy very rapidly because they're not limited by the gas pressure on the front face. And so these, we have convinced ourselves that with a sufficient number, we're showing 6, and we believe that 6 is probably a good number, as well as interior shear panels, we can make this as stiff as we need it to make it in order to get the right properties for the system. So here's an animation, a dynamic simulation of it, and we're showing here where the spacecraft is lined up on the angular momentum vector of the asteroid, but it is not a simple spinner, it's a tumbling asteroid. And so the instantaneous spin axis, shown in red, is kind of wanders around the angular momentum vector that is constant. And so what you see from the spacecraft, you see a continuous rotation. Here, however, we have lined up the spacecraft spin around a future axis that we know the spin velocity will reach. And so when the timer gets to 30 seconds, it will be perfectly lined up, spinning. The spacecraft will be spinning at the exact same speed as the asteroid. So with that approach, we're able to get zero relative motion at the instant that we grab. And so here again, at 30 seconds, the spacecraft motion, the asteroid motion relative to the spacecraft will be 0 at the moment of capture. And so we're just now coming up on the point where there's no relative motion. We trigger the bags and we capture the object, and then we go for a ride. And the spacecraft, as you see, starts to move in a significant way off both in rotation and translation. And this is a typical case where it rotates out along the equator, the belt line of the asteroid. And that's a good thing for us because that means the reaction control system thrusters on the end of the spacecraft have a nice long lever arm with which to despin and detumble this object. Now, it only takes a relatively few newtons of force over a period of hours to despin and detumble an object, even 1,000 tons, spinning at 2 RPM or more. But the key thing is that you need a long lever arm if you're going to be efficient in your use of propellant. Now, here in the lower corner, you see the so-called solar array deployment actuator torque, which is the key thing that is going to break on the spacecraft, is the joint where the solar wings hang off the spacecraft. And so when you accelerate the spacecraft, if there's too much torque on that deployment actuator, the solar arrays break off, and that's a bad day. So that is the most sensitive part of the spacecraft, and that is the thing about the spacecraft that is most in need of protection with our approach to grabbing the asteroid. So we have done a Monte Carlo simulation. So we simulated about 5,500 different cases with a wide variety of spin rates and shapes and angles between the angular momentum vector and the principal axes. And of course, it's the flapping motion of the solar array around what we call the y-axis here that is the greatest concern, because that when you yank on the spacecraft with the 1,000-ton rock, that's the mode that it's going to see the largest torque. So as you see here, we plotted the torque about all three axes, but it's the torque around that y-axis that is in every case the largest. And as we go out to 2 RPM, we see that we have a reasonable amount, because the vendors for the solar array deployment actuators have told us that with essentially no special effort, they can achieve 1,765 Newton meters of torque as their design limit. And so you see here that even in the case of 2 RPM, we're below that. And here we have tuned the stiffness of the bags, the pressure in the bags, and the number of shear panels and so on, in order to make the bag have the right elastic properties, the spring and damping properties, so that it achieves this performance. And working with our inflatable people, that have done the airbags on Pathfinder and MER and the new low density decelerator, those people tell us they can achieve these levels of stiffness and damping in the inflatable system. We have built a test bed, and that test bed allows us, it's a 1/5 scale, so we have a 2-meter Asteroid, which is actually a piece of styrofoam covered in rhino bed liner, which is what you spray the back of your truck, your pickup truck with to protect it. But it looks quite much like an asteroid. And we have a bag, and we have it's lined with Vectrans, which is fabric that we got actually left over from the last airbag system, which was the Mars exploration rovers. They had a whole bunch of fabric left over, so we managed to get that from them. And then we got an inflatable structure from a company that makes bounce houses for children's birthday parties. And they said, sure, we'll build you that, no problem. So we built this inflatable exoskeleton, and then we put the rock on the end of an 8 degree of freedom robot arm that has a force torque sensor at the point of attachment between the last degree of freedom and the rock. So that when the bag closes over it, basically it has this little spike that goes up into the center of the asteroid, and then there's a spin axis so that we can spin it continuously about one axis, and then we can move it in a cyclic way about all the other axes and thereby simulate tumbling motion. We measure the forces and torques on the spike at the point of attachment, and thereby measure the forces that are applied by the bag to the asteroid after accounting for the gravitational forces on the asteroid. And so that allows us to evolve the spin physics in a realistic way, so that we can basically just apply, Newton's law that says the time rate of change of angular momentum is the applied torque. We measure the applied torque. We know what the angular momentum of the asteroid is, so we can say what the future, what the next spin state is in every instant of time. And this will allow us to answer questions that you could never get out of a computer simulation, like, does the fabric snag on the rock? Excuse me. So we're going to put little Matterhorn rocks on the surface of our asteroid and see if we can get the fabric to snag, and what does that do when one side of the rock snags on it and the other side is slipping. We can answer questions like, do the cinch cords of the cinch winches, do they slide freely over the surface of the bag, or does the bag bunch up in one spot and limit the motion of the cinch cords so that the cinch cords don't completely close the whole bag, but they get bound up and the bag stops closing prematurely. Those kinds of questions you could never answer with any confidence in a computer simulation. And so with that, I think I'm done. Thank you.
Thank you, Brian. Okay, next up we have Lindley Johnson. He's the Near Earth Objects Program Executive in Planetary Science Division at NASA headquarters. He'll share with us a little bit about NASA's observation campaign.
Oh, thank you very much. It's nice to be here this time. I wasn't able to join you in the first part of this workshop, so it's nice of everybody to have delayed this for me to be able to join you for the continuation. Talk to you tonight about our Near-Earth Object Observation Program and how we are going to use that program and enhancements to it to be able to find the right candidate for this redirect mission. You've heard about the Grand Challenge already. We actually started working this Grand Challenge about a year ago, even though it wasn't announced until June of last year. The reason why it's very important to all of us Earth residents was made evident to us almost on cue in February of this year with the Chelyabinsk event in Russia, where a relatively small asteroid, only latest analysis showed it to be about 19 meters in size, exploded, entered the atmosphere and exploded over the city of Chelyabinsk, detonating with energy of something over 500 kilotons of TNT. Object that small, releasing that much energy is quite a sight. And it was captured, of course, this is probably going to be the best studied asteroid entry ever. The meteor and asteroid scientists have gotten spoiled by all the data they got from the dash cams of the Russians. But it did cause a significant emergency for the Russian population there in Chelyabinsk, and over 1,600 citizens being injured by the broken glass that was caused by the blast wave from this object, even though it detonated some 20 kilometers up in the atmosphere. The shock wave hit the town a few minutes later while everybody was looking out the window staring at this contrail that had been displayed across the sky and did some $30 million of damage. A few broken windows, but if you think of the temperatures in western Siberia in February, it was a bit of an emergency on their part to get the windows fixed to be able to keep their buildings heated. So even though it was a fairly small event as planetary impacts go, it still caught everybody's attention. So the Grand Challenge, as Michelle described earlier, is one part of the agency's overall asteroid initiative, the other part being the asteroid redirect mission. And what has been described here this evening, it's kind of interesting. We began with a vision of what we want to get to, and now we're showing you how we're going to get there. But the Near-Earth Object Observation Program sits right in the middle of both these endeavors. And we need to enhance the capabilities that we currently have with the observation program to accomplish these things. We are seeing increases in the program. It was increased to $12 million in FY12 before the redirect mission was even announced, and we were looking at another doubling of funding for the NEO program because it's a first step in this redirect mission endeavor, and that is to identify the asteroid that we are going to collect and bring back to the lunar orbit. That's been tasked to the existing Near-Earth Object Observation Program, which I and a few other dedicated individuals around the country operate. But it's already an international effort to identify and find the asteroids that are hazardous to the Earth. It's been a subject from the Committee of Peaceful Uses of Outer Space of the UN Office of Outer Space Affairs for a number of years now. I've participated in an NEO working group with that committee and to work the process by which the member states would work together to both identify a hazardous threat to the Earth and then figure out what we would do about it. The committee and how the UN operates has been somewhat misunderstood. The Committee on Peaceful Uses of Outer Space provides a forum for the member states to get together to talk about how do we cooperate, collaborate, and explore and make use of space for the betterment of mankind. So it's the ideal forum for the space-capable nations to get together and talk about how we would deal with a impact threat from space. And in this working group, we've brought to the committee, and now it's been brought on up to the General Council for approval of our recommendations of how the member states should work together. An international asteroid warning network would be set up, which is an enhancement of our existing network, which we've been running for some 15 years now, and a forum for the space agencies to get together and talk about mitigation or deflection capabilities to divert a hazardous asteroid off an Earth impact. Would be the Space Missions Planning and Advisory Group over on the lower right there. We would have this forum on a regular basis before a threat was ever identified, so that we could talk about what capabilities we would bring to bear to deal with that threat once it was discovered. And once a credible threat is found, then the member states would get together to bring the plan together that would then be taken into the international forum, informed with the Committee on Peaceful Uses of Outer Space, who might set up an ad hoc mitigation planning advisory group to work within the international forum to keep everybody informed and working together and advise any of the nations that might be affected by such an impact, which could be a large number. It wouldn't necessarily be any one nation, about what the space-capable member states are doing to avert that threat. And so that is what has been going on in the UN forums under the Committee on Peaceful Uses of Outer Space. There's no approval of a mission or authorization of a mission by the United Nations. It is work that is done by the space-capable member states with the sanction of that process and how it works together by the international forum and the committee. So back to, oops, did I go the wrong direction? Let's go back here. Yeah, I went the wrong direction. Okay, so back to the existing program that the United States has participated in and actually been the leading force for 15 years now. It started back in 1998 with the NASA committing to the House Committee on Science that we would find at least 50% of the large near-Earth objects, those 1 kilometer and larger in size. If the Earth were to get hit by one of those, it would be a 3-segment bad day for all of us. And originally the program averaged about $4 million a year through most of the last decade. But we reached that goal of finding over 90% of the 1 kilometer and larger near-Earth objects in 2010. However, in the meantime, as we studied what size object could still do significant damage to the Earth's surface in 2 or 3 studies that we did almost a decade ago now, we found that we really got to find them to a smaller size than that to significantly reduce the risk of casualties in an unwarned impact. Down to at least the 100-meter size, because even a 100-meter size object could wipe out a large region, certainly larger than a city if it were to hit the Earth in the wrong place. So the goalposts were moved in 2005 for us to find a 100-meter class. This is the language out of the Authorization Act, 140 meters in size in order to have a complete assessment of the risk of near-Earth objects to the Earth. And the goal of the survey would be to find 90% of those objects down to 100-meter class within 15 years. Since this act was released in 2005, that would be by 2020. We've got a ways to go to be able to achieve that goal. But our current program objective is to do that as soon as possible. Probably won't be able to achieve it by 2020 at the current rate and the current capabilities. But now, starting in last year and this year, the program is working with $20 million a year. But this program also detects even smaller size objects down to the size that we were talking about here, a 7 to 10 meter size object, or even smaller. We have actually found 1 or 2 meter objects as they pass through the Earth-Moon system. So we're able to detect those small objects as they approach the Earth, and those are exactly the type of objects that we are looking for this asteroid redirect mission. There are objects that are asteroids that are in orbits that are very near Earth's orbit, so that's what makes them easy to bring back. So it all kind of works together. Current observation program. First of all, we have two main data analysis and processing center. The first one is the Minor Planet Center. The Minor Planet Center has been in operation for decades. It is the International Astronomical Union sanctioned core center for obtaining observations from observatories around the world on all the small bodies in the solar system. So it's been in existence for decades, and it is an integral part of NASA's NEO program now, in that it does special processing on objects that are found to be in these orbits near the Earth's orbit, and gives us the initial orbit determination and alerts our systems when there's an object of interest to us, one that could be a potential hazard to impact in the Earth. That information is then relayed to the NEO program office out at the Jet Propulsion Laboratory, who helps NASA headquarters, first of all, with the program coordination. They do the precision orbit determination with all the observations that do come in. And this is a group of orbital analysts, astrodynamicists that do the navigation for spacecraft that we have throughout the solar system. They put the Cassini spacecraft through the rings of Saturn, for goodness sake, so I think they kind of know what they're doing in that work. So they do the precise orbit determination, project forward where these asteroids that we've discovered are going to be into the future with the observations that are obtained, and determine if there's any probability of impact for that object. Not only the Earth, by the way, but all of the other planets and large moons in the solar system. They can predict whether an object is going to be an impact hazard to Mars, which would be a very interesting planetary experiment to see. So those are our main processing nodes. Then we have currently, these are the ground-based telescopes along the bottom here that do the major contributions to search and detection and tracking of near-Earth asteroids. Linear has been with us since the beginning of the program in '98. Catalina Sky Survey is our most productive program. Came along about 10 years ago and bringing up the capability, and finds almost 60% of the near-Earth asteroids these days. Pan-STARRS, the University of Hawaii, has been coming online with a 1.8 meter telescope and is coming up on the step. Once we are able to go to a larger percentage of their time on the sky for asteroid search, they will be the most capable system. And then we've had the one space-based capability that we've been making use of. It was actually the Wide Field Infrared Survey Explorer was to do a science mission of the astrophysics science mission of mapping the infrared background of the sky to great detail in preparation for the James Webb Space Telescope. So it does that by continuously imaging the sky and taking multiple images, up to about 15 images over the course of a day of the same area of the sky. And then over the course of a year, it will image the entire sky twice. Well, we quickly realized that, that this instrument, even though it does it slowly than a more capable survey telescope would, is a very good asteroid detector, because you can take all those images that it collects, hundreds of thousands of images of the sky, and compare them one to the other and see what moves. And the things that moves are usually asteroids. So as it was in its main prime mission in 2010, started operations in 2010, we enhanced its ground processing capability to make an asteroid hunter out of it. And over the course of that year, 129 near-Earth asteroids were found by this system independently, and it also took observations of several thousand already known asteroids, both near-Earth asteroids and in the main belt. So it's become one of the biggest databases there is right now on asteroids in the solar system. It ended its prime mission at the end of 2010. We ran it for a few more months as an asteroid hunter, but then it was put into hibernation in the hopes of future use. With the grand challenge coming on board and our need to make the most use of any capability we could to find asteroids, we reactivated WISE as a dedicated asteroid hunter. It was woken up and put back into its stable attitude back in September, and now its optics are cooling down for it to begin imaging here within the next month. And we'll operate this spacecraft for as long as it will last, and be in the right kind of an orbit for about 3 years. We hope we'll be able to operate it. Currently, our sky coverage with those systems that we talk about over the course of a month looks like this. We can't, from the ground, we can't really search for these very dim objects in the full of the moon, so we lose about a week or so of time every month. But it takes about a month for the current system, for the current systems to cover most of the accessible sky. Now you'll see here that we're well covered in the northern latitudes, hemisphere. We lack search capability in the south, which would be nice to have a more capable search capability in the south. So, but these are how these systems operate. They basically tile the sky, starting one section of the sky, image it for a few seconds, and then move on to the next tile and across the sky, and then they will come back 30 minutes to an hour later, image that same part of the sky, bring all that data into their computer processing, and compare one image to another to see what moves. So this is the actual discovery imagery of an asteroid, and you can see it move from one image to another. There's about 30 minutes or so between those images. And we look for what moves across the sky. And did you see it? This is the discovery imagery of asteroid 2013 MZ5, which was the 100th near-Earth object that we have found in the course of our program. It was found by Pan-STARRS back in June of this year. And you see it from each 30-minute sequences move across. Current observing network is worldwide. This shows observatories from around the world that contributed observations to our network in 2012. Some observatories from some 46 countries. Some of them quite professional observatories. A lot of observations once we found an object for follow-up tracking actually come in from amateurs, very capable amateurs for certainly the larger asteroids. When we get down to 100 meters or so in size, it's really beyond the capabilities of even sophisticated amateur. But we've got some semi-pros out there too that even though they may not get paid for it, they have very capable equipment and a very dedicated hobby for some of these. And some of them make significant finds, like for instance Comet ISON, which we're hearing all about right now. If it survives a perihelion passage by the sun here in a week, should be a quite spectacular object in our skies in December and January. That was found by a team hunting for asteroids and comets in Russia. So they make significant contributions to the effort still. Currently, this is our population curve, accumulation curve, from when the program started in 1998 through this month. Right now we have 10,450 near-Earth objects in our catalog. That includes 94 comets, by the way, and that's why we call them objects versus asteroids, because some of them are comets. And 864 of those are larger than a kilometer in size, but you see that the discovery curve has tapered off. So that means we have found the larger part of the population of large objects. Our completion percentages based upon our population models, 96% are those a kilometer and larger, 60% in this bin, but as we get down to 100 meters and smaller, we have a significant number of objects to find and really need more enhanced capability to be able to do that. Our understanding of the population is based upon the modeling that's been done based on what's been found versus the time it's been found and the volume of sky that it's been found in. You can do statistical models on what the overall population is. This graph is this is a graph for the program that has everything on it. Down along the bottom here is absolute magnitude, the brightness of the detected object, roughly compared to its size, assuming average reflectivity. The Earth's atmosphere would protect us from any objects below about 30 meters in size, although Chelyabinsk, which would have been here on the curve, caused us to learn a few things about what we maybe need to worry about smaller objects. Tunguska back in 1908, which is the most significant event prior to that, was about 50 meters. The KT impactor, this is the one that killed the dinosaurs back 65 million years ago, and thankfully we only get an impact like that every 100 million years. 1 kilometer size objects, as we said, we have about 1,000 of them to find, and we're well up on that curve. If we go down to 100 meter class, there's some 20,000 objects out there to be found. 50 meters, 250,000. If we get down though to the size that we're talking about here, 7 to 10 meters in size, we're talking about millions of objects out there that could be classified as near-Earth objects. But those that would really be acceptable for such a retrieval mission are in the right kind of near-Earth objects, or maybe on the order of a few thousand. We have found 370 so far that fit in that size range, however not in the orbit that could be retrievable by this system. There's only about 14 objects that we know of right now that are in that type of orbit, and we are campaign is attempting to find more data on them. Enhancements that we're doing to build up our capability. We're working with the Department of Defense and DARPA and their new space surveillance telescope, so that it has NEO detection capability, so they can do that as a secondary mission. enhancing the capabilities of Pan-STARRS, Pan-STARRS 1 getting more time on the system so that it is able to dedicate more of its telescope time to search, and also helping the University of Hawaii complete the second Pan-STARRS system, so we have a second aperture that can be used. Also, we have a new capability that's in development called Atlas. It is making use of smaller aperture telescopes, but using very sophisticated cameras and software processing to more rapidly cover the night sky, so that it would be able to, with a couple of these systems, be able to cover the entire night sky, not the entire sky each night. It won't go as deep, in other words, to see dim, large objects far away that are very dim, but would find any object that was close to Earth down to this size of 10 meters or so. That'll come online in 2015. With these enhanced capabilities, we expect the discovery rate of ARM candidates to be increased. We find about 2 a year now that meet the criteria that is needed for this retrieval mission. We think the capability with these enhancements, our studies show the capability will be increased to at least 5 per year. So over the 3 or 4 years we have until the launch of such a system, we should be able to find at least 15 more acceptable candidates for the mission. Another important aspect, as Brian went into, is being able to characterize these near-Earth objects. We used a number of techniques, whatever is able to observe the objects to do that. Radar is an important capability, but we also use a lot of optical techniques to understand more about the size and mass of these objects. If there can be a significant difference in the size that you don't know until we do this more enhanced characterization. It could be a very large dark object, and so be outside of the capabilities of the retrieval spacecraft, or it might be a very small but bright object, and so it would meet the size that the arm could retrieve. So final selection of the target will depend largely upon our ability to characterize it, and the upper bound may be, we have to work with what the upper bounds might be to be within the capability of the retrieval mission. Radar, as I said, is one of our most important capabilities to do this. And we should be able to now rapidly get the radar on these objects as they are discovered. In the past, a small object, we really didn't care about it. We let it go by. But now that we are interested in seeing these things for the retrieval mission, we will bring those radars on as rapidly as we can after the object is discovered. We have to discover the object optically. You can't do it with radar. You just don't get the signal noise return. But once it's discovered optically, then the radar, the two planetary radars can be brought up on it to more fully characterize it. And that would be the best way to be able to characterize those things. So our characterization enhancements, first of all, the radar, getting as much time on those as we can, and also streamlining the rapid response to get observations on an object as soon as it's discovered. Also, increasing our capabilities with the NASA's infrared telescope facility on Mauna Kea and Hawaii, both in rapid response as the same with the radars, but also improving the instrumentation that's available for characterization. And then, as I mentioned, we've already reactivated WISE. As I said, WISE is important as a discovery tool, but it's also very important in that for characterization, in that it operates in the IR bands. And with 2 IR bands, you can get a more precise determination of its size, estimate of its size, than you can optically. Bound it within about 20% versus maybe 200% with just optical observations. So these capabilities will add to our capability to find not only a target for the ARM mission, but also improve our capability to find hazardous asteroids, which is what we've been in the business for a long time and will continue to do. rapid response after discovery of the object is key. And so these objects that we find now that we're undertaking this mission, these objects that we find in the future, we'll have better characterization of those objects than we did previous to this time, because we just weren't focused on the small objects because they're not seen as a hazard to the Earth. We'll bring all the assets that we can to bear on this mission in the next 2 or 3 years, and work with both interagency and international entities on this capability. And so with this increase in NEOs, both as a hazard to impact to the Earth and the opportunity that they pose for not only exploration but potentially future resource utilization, this is a big mission area now for our planetary sciences, not only for NASA but around the world and in the planetary science community. Thank you.
Thank you, Lindley. Our final presenter tonight is Chris Moore. Chris Moore is the Deputy Director of the Advanced Exploration Systems in the Human Exploration and Operations Mission Directorate at NASA headquarters. Chris led the RFI selection process, and he's going to give us a brief overview of that.
Good evening. As Wendy said, I'm going to talk about the RFI process and explain why we're all here. So when we first started this Asteroid initiative, we realized we'd never done anything quite like this before. So we knew that we had to get the best and most innovative ideas to help us plan the missions and the flight systems development. We also realized that defending our planet against the threat of asteroid collisions really involves everybody on the planet. Everybody's got a stake in it. So we wanted to involve as many people as possible. So we cast the net widely for ideas. We released an RFI in June, and we requested information in 6 main areas. And the RFI was open to everyone, individuals, companies, universities, other government agencies, international partners. We did receive 402 responses, and we went through a process of evaluation to select the most promising and interesting proposals to discuss here at the workshop. Here's a breakdown of the responses by type of organization, and we had about 40% from the general public, which was really gratifying. We had people who would sit down in front of their computer in the evening and type a few lines describing the idea that they had. And so we really captured the interest of the general public. The other large segment was from small businesses who are interested in stimulating new markets and asteroid resources and new technologies. And we had about 10% from larger corporations, the rest from NASA centers and some observatories and universities. Here's a breakdown by the 6 areas, and the workshop is structured around these areas which were in the RFI. But the area with the most responses was the asteroid deflection demonstrations, followed closely by asteroid observation. And the one with the fewest responses was the crewed systems. We also got responses from all over the world, from 16 different countries. There was a lot of interest in Europe and from the UK, but we got responses from as far away as Uganda and Finland. So it was really great to see that. We touch people around the world. These are the criteria we use to decide which ideas would be presented here at the workshop. We had a team of NASA reviewers who read all the proposals, and we tried to assess them relative to these 4 factors. The first factor was how relevant was it to the objectives of the RFI? Did it address one of the 6 main areas, and did it demonstrate a clear understanding of these areas? The second factor was how much impact would the idea have on ensuring mission success or accelerating asteroid observations, reducing risk or improving performance of the system. Was it a really innovative idea, and most importantly, was it feasible? Was it something that we could incorporate into our plans? The third factor was maturity. Some of the ideas we got were really great ideas, but they were way out ideas that would require a lot of development. So we had to decide if it was feasible that these new technologies could be matured in a reasonable time frame to incorporate into our mission plans. And the fourth factor was affordability. Can the concept significantly improve the affordability? And we also tried to involve as many people that we hadn't talked to before. We didn't want to talk to the usual suspects because we know what's going on in the NEO observation program, and so we wanted to get ideas from outside the usual sphere. So that's how we arrived at the 96 briefings that you'll hear, and the abstracts of all of these responses are archived on the web, so you can download them if you're interested. So what do we want to get out of this workshop? We've asked the leads for each of the groups to summarize the most promising ideas and describe any technology development that may be needed to mature these ideas to the point where they can be incorporated into designs. Are there any relationships or linkages that could help with system or mission integration? And we really don't want this to be just a bunch of presentations. We want to encourage discussion. That's why we're here. And we'd like you to come up with findings and recommendations on how to use all these great ideas. So we have a wealth of data, and we're just trying to synthesize all these ideas into products that we can actually use in planning our next steps. So I think that we can reflect on the importance of this asteroid initiative in history. If we're successful with the redirect mission, for the first time we'll be rearranging the solar system to bring humanity greater prosperity and security. Greater prosperity by using asteroid resources, greater security by protecting our planet from the threat of asteroid collisions. And this is pretty incredible if you really stop and think about it. The solar system's been in existence about 4.5 billion years, and the planets and the asteroids and the comets have been circling the sun all that time, moving under the influence of gravity, but not really perturbed by anything that happens on Earth. And now we're a spacefaring species, and we have the capability to shape the solar system for our own purposes. So we tend to get excited about all the science and the engineering and the technology that goes into this mission, but let's also reflect on how it conveys the human spirit to explore. So all of you are helping us take the first steps in this great endeavor by being here and telling us about your ideas. We do appreciate and value your inputs and the time you've devoted to this workshop. So we look forward to a lot of great discussions, and we're really excited to see this program get started. So that's the last presentation for this evening. We're going to open it up for questions now, and I'll turn it back to Wendy.
Thank you, Chris. And thanks to all our presenters this evening. We're running short on time, so we probably only have time for one or two, if there's anyone.
Hi. I had a question for Lindley Johnson, I guess. Are there any plans to actually extend assets deep into the southern hemisphere? Chile or South Africa or even, for that matter, the South Pole? I mean, it seems like it's a missing gap to the program.
Well, over the course of time, it's not so important that we're not searching from the southern hemisphere because we hope to discover these objects, many years before they might be an impactor. But that aside, it would be good for some of the southern hemisphere countries to join the effort and add capability both for search and tracking of newly discovered objects.
We have one over there.
What happens after the workshop? What happens to the material? How does it get fed into headquarters planning and so forth for actual mission?
So there's actually two routes that are currently planned, no pun intended. The first is the leads for the study efforts that were discussed are present and here, have been asked to listen and incorporate any of the highly rated ideas in the synthesis Friday afternoon into their studies. The second is that the robotic concept integration team that has been chartered and is being led by Jim Ryder at Marshall has been asked to perform a figures of merit assessment, including ideas that come out of this workshop, so that we're ensuring that we've got a quantitative analysis of an integrated system and a mission concept that brings the best and brightest forward. I would also say that the robotic concept integration team has been asked to make recommendations on any future activities that we might offer as a follow-on to this RFI to gain more analysis in specific areas that fit into the results of the FOM analysis. I'm not sure if that's clear enough, but in our industry day, we will announce any changes in our plans as a result of the robotic concept integration team, as well as the internal studies that continue to evolve.
Thank you. And I also believe that we have a question online.
So there's been lots of discussion online and a few questions on Twitter about mission schedule and cost. Michelle, could you summarize the asteroid redirect mission timeline and briefly address the cost?
Is it possible to bring my slides back up? There's a slide 4, which just re-articulates the alignment strategy that's been discussed since Robert Lightfoot, our associate administrator, first discussed this mission concept. Sorry. Slide 4, please. So this chart, actually, if you watch the versions as we continue with our concept development, it evolves over time. You can see the addition of the NeoWise activation in this version, as well as the anticipated enabling of a robotic mission launch in 2018, which includes the solar electric propulsion demo, and the crewed EM1 mission of SLS and Orion. So the basic strategy is to leverage ongoing activities inside the organization, inside NASA, with key strategic investments in other areas to enable this strategy to occur. So I would say that our current studies are looking at technical and programmatic feasibility. These timelines will change as we gain more data, including on targets like Lindley Johnson suggested or presented his observation asset plans that are being put in place. And as this timeline matures and we gain a better understanding of technical and programmatic feasibility combined, we'll have better answers to that question.
Thanks again, Michelle. Okay, so we're out of time, but there have been some great conversations going online, and we want to try to keep that going. So we want to remind everyone that the hashtag NASA Asteroid, and that we will have chat rooms and hashtags for each session. And so keep the conversation going. And this concludes our plenary session. And we look forward to having everyone back tomorrow morning at 8 a.m. for the session topics. Thank you.